We're gonna make our classes, first thing we need is we need the high and the low. So somebody help me out, what's the high, what's the low?
The low is 25.
25,
65?
65? How many classes did they say split it into?
7.
7? Somebody help me out, what's 65 minus 25 divided by 7? Ms. Clark thought we were done making these silly things that she loves so much. 5.7, what do we do with that? Round it up 6, so that means our class width is going to be 6 each time. We start with the low, 25, we go up 6 from there, 31, 37, 43, 49, 55, 1, 2, 3, 4, 5, 6, 61. I didn't add wrong anywhere, did I? How do we know what the upper limit on this class is going to be?
Minus 1 from
All right, so you just go back 1 from that, what do you get?
30.
30, 36, 42, 48, 54, 60, and on this last one, we just add 6 to that number right there, 66, ignore that.
Put 55.
Sorry. 54. We'll make a tally so that you can just read me, then we'll do the frequency. Somebody just read me off the list, and I'll start tallying them up.
40, 45, 54, 41, 43, 31, 47, 30, 33, 37, 48,
38,
48,
48.
57, 52, 45, 38, 65, 25, 39, 53, 51, 58, 52, 40, 46, 44, 48, 61, 47,
47?
49, and 57.
So we got 2, 2, 6. How many were there? How many numbers were there? 30? 9, 6, 3, 2. That's 5, 11, 20. Plus another 10, that's 30. So it looks like we got them all. So this draw frequency histogram, that's part A. So the first part we want is a histogram. We're going to use this to make a histogram. Frequency goes over here on the side. Looks like we're going 2 to 9. So I'll just go by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 10. Just writing those in there. Over here for our bottom, several different ways you can do it. I like using the midpoints just because it's pretty easy to find the midpoint each time. And just putting the midpoints on here. You could, go 25, 30, 36, so on and so on, and just do it that way. It's probably easier using the midpoint, so that's what I'm going to do. Somebody help me out for this first midpoint, and I can find the rest of them. We add these two together, 25 plus 30, then we divide that by 2. that give us?
27.5.
27.5. So that's gonna be my first one, 27.5. And then to get the rest of them, all I'm gonna do is add 6 to that. Just the same as the class width that we found. So that'd be 33.5. Next one's 39.5. Next one's 45.5. Next one's 51.5. Next one, 57.5. 1, 2, 3, 4, 5, 6. We need one more. Next one is 63.5. My numbers don't look too good. My pen's not writing right. Then we just make our bars for each one. First one's 2. Go up 2. Second one's 2. Third one's 6. Next one's 9. Next one's 6. That bar there is not very good. Next one is 3. And the last one is 2. So our histogram should look something like that. Letter B says find the mean and standard deviation of your sample. Several different ways we could find the mean and standard deviation. Probably the easiest way, all those numbers, we really don't want to make this chart out all the way out and find the mean and standard deviation that way, do you? Is that the way we want to do it? Probably not. Use your calculator. What you'd have to do use your calculator, Molly, will you look on my calculator and see? I'm not sure if I put it in the list or not. Look at list 1. I may have put in it. You're going to put all those numbers in that list, in one of your lists on your calculator. $40, $65, $45, $25. So all Molly's going to do for us is she's going to hit, to find the standard deviation stuff, we hit stat, go over to calculate, down to 1 bars. You already did it, right? Confused me because you did it ahead of me. It's all, my calculator is different than the rest of yours. You guys would have to then just put in list 1, L1, and hit enter. All you gotta do is go down to calculate, hit enter, because I've already done it. And we want to find the standard deviation. Let me read this again. Randomly sample 30 people, so we're doing a sample. So we want to find the standard, or I'm sorry, the mean, and then the standard deviation. What's X bar? 45.86, 45.9 we'll say. And what's the S sub X?
9.46.
About 9.5. Does it look like the mean should be somewhere around 45.9? Does it look like that would be sort of in the middle of the data? Yeah. Part C says compare the mean and standard deviation of the sample with those previously discussed. So we're just comparing it with theirs. Their mean was 48.7. Ours was 45.9. What do you notice about their mean compared to our mean? It's higher. Good enough. All right, it's bigger. Their mean was bigger. Their standard deviation was 8.6. Ours was 9.5. What do you notice about their standard deviation compared to ours? It's lower. Good enough. All right, 2 separate samples. The main thing here is they said theirs was normally distributed, so it was sort of symmetric. Does ours look symmetric? Does it look like this is about symmetric? Yeah. So could we probably assume that if we took another sample that it should come out somewhere or somewhat symmetric. Probably so. Next question. No others? That one didn't even really have a whole lot to do with what we did last time, did it? That was sort of going back to a lot of the previous stuff. All right, just to go back over some of this. This is stuff you wrote down last time. Got to make sure that you have this. Got to make sure that you have a calculator. I don't even want to show you, Sydney, how to do this stuff out longhand, all right? So make sure you have a calculator. Not borrow one from somebody. Again, if we're looking for the area to the left, so if I have my normal curve, looks something like that. We're looking for the area to the left. That means from some number down that way. This is what we punch into the calculator. We wrote all this down last time. Remember the negative 10,000, that's just some random number that we're picking way out here to the left so that we put guidelines on it. It goes from this up to this. You probably don't have to go down to negative 10,000. You could probably put in like negative 200 or something, and that'd be plenty. So that's to the left. The other, next thing we wrote down was to the right. So if we're looking at this normal curve, and I want you to be able to draw these each time. A lot of the stuff that we do for the rest of the chapter, draw this normal curve. It doesn't have to look good, but if we're looking for area to the right of some number, then I know, hey, I'm going from here. And just shade that in so you have some idea of what you're actually looking for. We're going from there over. We start with the z-score. We put in the z-score first, comma, then the high limit, which we just make up some random number again. I use 10,000. And then if we want area between two z-scores, so something like this, we want that area. Do the same thing, you just put in the low z-score, the high z-score, punch it into your calculator. Remember, you're always going to second vars. I should have mentioned that at the beginning. Second vars, normal CDF, and then you punch all that in. So that's just going back over the stuff that we covered last week. What this section's going to cover, finding probabilities. That's why Jacob's paper confused me, because he already had probabilities. Well, I told you last time the area under the curve and the probability are actually the same thing. So we're still doing the exact same thing. All right? One thing you got to remember, changed on me. One thing you got to remember with this is you have normal distributions. That's using raw scores. Raw scores. So your numbers might be like 750, 220, 180, whatever. Then you have standard normal distributions. That's when you're using z-scores. So you have normal distributions. That's where we're just using whatever the numbers are that we collected from the data. Then the standard normal is when we change them to something that's standard to look at. So you got to be able to distinguish between those two, raw scores and z-scores. Probability in the normal distribution, or normal distributions, hopefully you can tell what that says. If a random variable x is normally distributed, you can find the probability that x will fall in a given interval by calculating, go ahead, you're right. Calculating the area under the normal curve for that interval. Nothing real new there. So if we're calculating that, we're finding the probability x is less than 600. It's going to be that area right there. Notice here we're using raw scores. We're not changing it to the standard normal, which would have like 0 as the mean, then 1, 2, and go by standard deviations. Probability for standard normal, either use a chart. Does anybody want to use that chart? Do I need to get it out and explain it again? Yes, no, maybe? Does anybody not have a calculator? Anybody want to say anything? So if I'm using the chart, first thing you got to do is you got to change everything into a z-score. Then if we want to find the probability, let's say our probability is x is less than 600, like that last one said. First thing we got to do is we got to change that 600 into a z-score. Maybe it comes out to be, as a z-score, that 600, when we change it using this formula right here, it comes out to be 2.379. Then what we do is we look on this chart, we go to 2.3 over here on the side, and that's going to round off to about 2.38, because our chart only goes up to 2 decimal places. So we go down to 2.3, go over to 8, and it comes out to be 0.9918, I think.
What I thought I read.
One three. So if you're using the chart, just match it up. You got 2.3 on the side. You got the first 2 numbers on the side. Then you go to the next number across the top, and it will tell you the area. Bad thing with using the chart, the chart only tells us area to the left. Area to the left. So if we want to do area to the right or area in between, we got to do other things. We got to find a couple of areas and then either add them or subtract them. Probability of a normal distribution, same idea, exact same thing. So it's the same normal distribution. We're our standard normal, we're always using z-scores. Normal, we're using the raw scores. That's the only difference. Notice that standard there. When it says standard, that means you're doing z stuff, z-scores. Don't let this confuse you. You're still doing, it's basically the same thing, whichever one you're doing. It's just one, we're always using those z-scores, and we know our z-scores are 99.9% of the time going to be between -3 and 3. When we're using just the normal distributions, our numbers could be anything. Still doing the same thing that we did last time. Still finding that area, because the area under there, since how much is a whole curve? Guarantee this is a question on the next test. What's the area under that whole curve? 1. So it's 1 whole. And then we're just finding what part we want. So if we have something like this one, this is that example that I had at the beginning. If the mean is 500, the standard deviation is 100. Draw this little, notice, draw the little curve, put in your mean, 500. We want at 600, that's the number we want. We want the area this way. This is what I want you to be able to do. Draw that, so you get an idea of what your area, what your probability should come out to be. Right now, without doing anything, I can look at this and I know my probability is higher than what percent. What's the probability it's gonna fall in that shaded part that I have there?
60.
It's gonna be higher than what for sure? 50%. Because right there would be 50%, right? So when I get an answer, and I come up with something like this, what do I know? I screwed up somewhere. Right? Because I know that my probability should be higher than 0.5. So if you can draw that, it'll make things better for you so you can know for sure that you're not messing up somewhere. Here, all they're doing is changing this into z-scores. Change this into a z-score. Remember, use x minus mu over sigma. In this case, our x was 600. So we do 600 minus our mu was 500 over the sigma, which was 100. They made one that was easy here. That's 600 minus 500 is 100. 100 divided by 100 is just 1. So that means our z-score for 600, the number that we're looking at, is just 1. So we could punch that into our calculator and just use a z-score of 1. That's changing it from the normal distribution to the standard normal distribution. The survey indicates that people use their cellular phones on an average of 1.5 years before buying a new one. The standard deviation is 0.25 years, or a quarter of a year. A cellular phone user is selected at random. Find the probability that the user will use their current phone for less than 1 year before buying a new one. Assume that the variable x is normally distributed. So we're saying that all this, we believe that it's normally distributed. Right here in the center is our 1.5. That's our mean. Then we go up to 1.275, just adding on one standard deviation. That's 75. And then up to 2, then up to 2.25. And we could go down, doing the subtracting off the standard deviation, go up 3, down 3 for all our standard deviations. We're trying to figure out what's the probability that would use their phone less than 1 year. So 1 would be somewhere like right in here. This would be 1.25. That would be 1. So we want less than a year. That would be that area right there. If I draw that little graph and I can figure that out, should that be a real big area? Give me a percentage that might be. Make a guess. Ain't nothing wrong with 0.2, 20%. All right? I know it's going to be less than 50%, right? It's going to be pretty small. It actually is, that's 1 standard deviation below, that's 2 standard deviations below. So that'd be at 2 standard deviations below the mean. Well, anything that's more than 2 standard deviations below the mean, we know is what? Unlikely, right? If I could spell unlikely. So we should probably have a fairly low percentage here when we figure this out. And I'm going to show you 2 different ways to do this real quick. So have your calculators out to make sure you can follow along and do it. Normal distribution looks like that. If we change it over into z-scores, it's going to look like that. We're going to be at -2. That's going to be our z-score right there, that -2. Just switching it over using that little formula. 1 minus 1.5 divided by 0.25. We're looking for this area. What's the probability that it falls in that range right there? We already know it should be unlikely because it's 2 standard deviations below the mean. It comes out to be 0.0228. If we take our calculators, 2 different ways we could do it on our calculators. And I'm going to show you this. Oops. First thing, We hit second VARs again, just like last time. Go down to normal CDF, hit enter. Molly's calculator is going to be messed up, and she's going to look at it like, what in the world is this? That's the newer calculator, and it just sort of gives you a list, right? So you just have to put in those items. We changed everything into the standard normal. That's what we were doing last time. Everything was in standard normal. So all we're going to do is take this, and I'm not used to using this calculator now. What do we put in? Because I'm used to using that one. What do we put in once we hit second VARs and it says normal CDF? We put in our, do we put in the mean?
What is our lowest or?
Oh, we put in the lowest and the highest, right? Just put in the two limits. So we put in the lowest and the highest. What's our lowest going to be here? Negative 10,000. So I put in negative 10,000, comma. And then our highest that we want this time is negative 2, close the parenthesis, hit equals. Does your calculator give you that answer? Something pretty close to that. Now the other thing I'm going to show you, that's if we change everything into a z-score, into standard normal, right? If we change everything into that. If you don't want to change everything into that, there's another way you can do it. And that's what I'm going to show you right now. So if we hit second VARs, go down to normal CDF, instead of changing this and then using the standard normal stuff, we could just leave it in the normal distribution and we should be able to get the same answer. And I got to remember which things we put in. This time, instead of just putting in the low and the high, now you also got to put in the mean and the standard deviation. Sorry, my sigma doesn't look too good. And I got to remember which order to put it in. Tell you what, instead of me sitting here trying to guess, let's do this. So if we just want to use the calculator and we don't want to take the time to change it to standard normal, we can punch it in like this. You punch all the same things, normal CDF again, put in the lower limit, the upper limit, then you put in the mean and the standard deviation. All right, so you just put a comma, and it's, I should have put a comma here.
The comma between everything.
Yeah, a comma in between each thing. So I'm going to give you, I'll let you go ahead and copy this down in your notes as soon as I get done messing around here. So you got lower limit, comma, upper limit, then a comma. Got to write that in there. Then a comma after the mean, your standard deviation, then you close the parenthesis. So instead of us changing everything into a z-score, instead of us changing everything, you can use that right there, and that'll do it all for you on your calculator. Now, if you're using the chart, then you have to change everything into z-scores. So if you don't have a calculator, and you're not going to bother to try to find one, then you have to change each thing into z-scores, because the only thing that the chart gives us are z-scores. get to. All right, that sounds like that came back here. Do I have that? So again, we could change it all into Z-scores. You could use the chart. Find that area. Could use your calculator, doing the same as we were doing last time. That's going to give you the probability. Probability at X is less than 1 year, so probability that the person keeps their phone less than 1 year before they get a new one is about 2%. About 2% of the people is going to have their phone for less than a year and then get a new one. It's probably, most of those people probably weren't teenagers, right? Because we know how you guys work. Katie gets a new phone and it's cool, and then Jacob's dropping his phone on accident and watching the screen break. Oh, I got to get a new phone.
I can afford to do that.
If we wanted to do it, let's go back for a second. If we wanted to do it the other way in your calculator, if you grab your calculator and we use, just leave it in the raw scores, or just punch it in the raw scores in your calculator. All you're going to do is hit second, vars, go down to normal CDF, and we're going to punch in the low limit, the high limit, the mean, and the standard deviation. So we don't put in these numbers. We don't even worry about this stuff over here. We just punch in the raw scores. So our low limit, still negative 10,000, comma. The high limit this time is 1, comma. Our mu, our mean is 1.5, comma. And our standard deviation is 0.25. Close the parenthesis, hit enter. It should give us that same number, does it? Yeah. Now, sometimes it's going to be just a little off if you're using the chart, or if you're using the calculator. It'll be, this might be 0.0227 instead of 0.0228 or something like that. So it might be just a little off. But you could do either one, raw scores or Z-scores. Let's try this one. Average speed of vehicles traveling on a stretch of highway is 67 miles per hour with a standard deviation of 3.5 miles per hour. If a vehicle is picked at random, what is the probability it is violating the 70 mile per hour speed limit? Probably, this is probably wrong, and I probably changed this last year. Or last couple of years, because the speed limits on a lot of highways went up to 70 in the last 3 or 4 or 5 years. So I probably changed that. This probably at one point, it probably was 65. That would make more sense, right? Speed limit's 65, the average is about 67 probably, because you don't see many people out on the highway going 55. Okay, but we're going to go with the 70 just to go with that. So our mu this time, 67. Our standard deviation, our sigma, 3.5. And we're going to do all this stuff. We're going to sketch the graph, find the z-score, find the area, interpret the results. Again, we're going to find the z-score only for the simple fact that you need to know how to find z-scores still. Do we really have to have the z-score to be able to find the area? Not really. All right, so we're going to find it and use it both ways, see if it comes out correctly. First, we're going to sketch the graph. When I'm saying sketch the graph, this is all you're going to do. Draw your little curve there. Michael was pretty impressed. That curve was pretty good, wasn't it, Michael? That was like the best one I've ever drawn, I think. You might just have to stop and admire it for a while. Right here in the center, 67. Because that's our mean. If we want to actually draw the graph, and on most of them, I don't want you to draw everything. On some of them, you might need to draw all of it. But if we wanted to go out 3 standard deviations on each side, all you're going to do is take that 67 and add the sigma. So 67 was the mu. Our standard deviation was 3.5. I'm just going to add 3.5 to each number. So that give me 70.5 for one standard deviation above, then 74, then 77.5. To go down, again, I don't expect you to write in all these numbers every time. The mean will probably be good enough and the x that you're looking for each time. But just to show you how to do it, here we subtract off 3.5, so what, that'd be 63.5, is that right? Yes, no, maybe? Subtract 3.5 from that and we get 60. Subtract 3.5 from that and we get 56.5. Hopefully I subtracted right on all those, didn't I? So we sketched the graph. That's what the graph would look like. Again, this is our mean right here. We want to find the z-score for 70 miles per hour. So that's x, that's our 70, minus the mu, which is 67, divided by 3.5. Somebody help me out with the calculator. 70 minus 67, I can do, that's 3. What's 3 divided by 3.5?
0.85.
So if we're looking at this, if we're just using the raw scores, we want 70 miles an hour, find the area to the right of 70 miles an hour. 70 miles an hour would be right in here. We want to find this area if we're just looking at the raw scores. If I wanted to draw another graph using the z-scores, remember the z-scores, that's horrible. The z-scores, 0 is always going to be the mean, then we go 1, 2, 3, -1, -2, -3. We change that 70 into a z-score 0.85, that's going to be somewhere about in here. So we're looking for that area. So if we're just looking at the normal curve with the raw numbers, it's going to look something like that. If we're looking at the z-scores, the standard normal curve, it's going to look something like this. Basically, they look like the same thing, just your scale's different. They should look exactly the same. Mine doesn't, but they should look exactly the same. Just the scale numbers being different. We want to find the area to the right. 2 different ways we can do this. First, let's do it using the raw scores. If we're going to use the raw scores in your calculator, you're going to punch in the low limit, the high limit, the mean, and the standard deviation. So our low limit this time, our low limit is what? 70. What's our high limit going to be? 10,000. Our mean, 67. And our standard deviation, 3.5.
Is it 10,000 every time?
10,000 or negative 10,000, depending. If, here, if we're going out this way, that's why I draw the graph every time. Because if we're going out this way, then we want to go out that way as far as we can go. It doesn't have to be 10,000. It could be, 2,000 or
Will
something.
they tell us it's different, or
Now you just have to decide that by what you're trying to find. So if we're finding the area to the right, then we're going to use 10,000. If we were finding an area to the left, we would want to use our low limit as negative 10,000. If we were finding the area between two numbers, like that area in there, then we're not going to use either one of the 10,000s because we're going to have a low limit and a high limit. If I get this, what'd that area come out to be?
One, wait, 0.1957.
Anybody else get that?
Have the negative that, but I don't know if that's good.
How would you, negative
Or not the same thing.
0.1957? Have to check it, let's check it here in a second, because should an area ever be negative?
No, that's why I'm questioning.
Let's do it the other way using the z-scores. So if we're using the z-scores, instead of the raw scores, we're doing standard normal. Instead of punching all four of these in, all we're going to punch in is the low limit and the high limit. But we have to change them into z-scores. Well, our low limit this time is 0.85, and our high limit is 10,000.
I switched the numbers.
Switched them around somehow. What'd that area come out to be?
.198.
Something like that. Are those pretty close to each other? Yeah. Because if we just look at percentages, this is about 19.5%. That's a little more than 19.5%, but they're pretty close. So when we change it to a z-score, when we got this 0.85, we probably rounded it off quite a bit, and that made us get higher a little bit. Now let's interpret this. If you can remember all the way back to what we started with, we were finding the probability of picking a car that was going faster than what? 70. So what's the probability, about what percentage of the time will we pick a car that's going faster than 70? About 19%. In between 19 and 20% of the time, if we just pick a car at random, say that car right there, it's going to be going faster than 70 miles per hour. And again, so with just this information, about 20% of all cars are speeding on a normal highway, right? Now that's with this information, saying that the mean was 67 miles per hour. We probably can guess that the mean's probably not 67 miles per hour on 70, right? Where the speed limit's 70 miles per hour. So if the mean went up, that would mean, that would give us a higher percentage in this, so we could probably guess that in between maybe 30% of all cars, if we were just pick at random, 3 out of every 10 cars out on 70 would be speeding. Survey indicates that for each trip to a supermarket, a shopper, so this one will help Katie, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes in the store. Length of time spent in the store is normally distributed and is represented by the variable X. The shopper enters the store. Find the probability that the shopper will be in the store between 24 and 54 minutes. So if we want to, let's just do this on the calculator before I switch slides. If we want to do this on the calculator and we just want to use the raw scores, we don't want to change the z-scores. You're going to hit your second bars. We're going to put in our low limit, our high limit, our mean, and our standard deviation. What's our low limit this time? 24. What's our high limit? 54. What's our mean? 45 minutes. And our standard deviation. Punch all that in, and that's going to tell us the probability that a shopper is in our store between 24 and 54 minutes. What it come out to be?
0.7333.
Anybody else get that?
I got it.
So about 73% of the time, the shoppers are spending between 24 and 54 minutes in the store. If you own a store, might this be something important to know, how long they're spending in your store? Probably so. You want to know, number one, for sales, okay, what can I do to sell more so I can make more money? Number two, you might, if you got somebody that's spending an hour and a half in there, you might want to keep an eye on them because they might be trying to get away with something.
So this, like, that's a way to find the answer, right? The other way is just a different way to do it?
Yep.
Okay.
So if we wanted to change these into z-scores and punch it in like we were doing last class using z-scores, then what we'd have to do is change each of these into a z-score. So we take 24 minus 45, somebody have their calculator out to help me, divided by 12. What's 24 minus 45 divided by 12?
I got negative 1.75.
All right, and then we would take 54 minus 45 divided by 12.
I got 0.75.
0.75?
So we don't have to do.
You don't have to change them into z-scores, but you have to know how to change a number into a z-score, because that's going to be part of what I'm going to ask you at some point, is how do you change that into a z-score. So now we could punch it in just like this using the z-scores. Only with the z-scores, we would punch that in. Negative 1.75 is our low limit, 0.75. If we're changing them into z-scores, what's our mean? What's the mean every time when you're looking at the z-score chart? 0. And what's our standard deviation? So z-scores, mean is 0 and it goes up by 1s each time, or down by 1s. So we could punch all that in. It should give you that exact same number. On your calculators, they got it set up so you could just punch that right there in, and it should give you that same number. All right, this is a standard normal curve using z-scores. This is just a normal curve using raw scores. Let's see if we got that right. 0.7333. Yeah. So here's what it looked like. I don't know if I have it on here or not. Let's see. If we change it all into z-scores, it looked like that. Exact same graph, raw scores over here with the actual minutes, z-scores over here. What you guys do, lie to me and oh, no. So if we were using the chart, we would have to find, because it only gives you the area to the left, we'd have to find all of this area. And then we don't want this part out here, so we'd have to subtract that off. But if we're using the calculator, we don't have to do that. With the calculator, we could just punch in the numbers. $200 shoppers enter a store. How many shoppers would you expect to be in the store between 24 and 54 minutes? How would we figure that out? If we got 200 shoppers and you just told me that the probability a shopper was in the store for 24 to 54 minutes was that, what would we do with those two numbers to figure out how many of those shoppers are going to be in the store 24 to 54 minutes? Just do one thing is all you do. If I told you 20% of all the cars are speeding and we watched 200 cars, what would you do to figure out how many of the cars were speeding? What mathematical operation? Just times. Just times. So you take 200 times 0.7333. How many of those shoppers do we expect to be in the store between 24 and 54 minutes?
147.
So about 147 of the shoppers we expect to be in there that long. So that's all you do if you're looking at, this is like going back when we were doing probabilities. If you're looking at this, or not when we're going back to, because we're still doing probabilities. If you win, let's say, every single time that a shopper stays in the store, for some reason, Miss Clark and Sydney don't have a life, and they're in there betting with each other. I bet this shopper stays in here between 24 and 54 minutes. And they want to know, well, out of every 200 shoppers that they see, 147 of them are going to be in the store. So 147 out of that 200 is going to be in the store between 24 and 54 minutes. That's what we got there. Find the probability shopper will be in the store more than 39 minutes. If we just do this real quick, we're just going to punch it in the calculator. Our low limit, it says more than 39 minutes. So our low limit is 39 minutes. What's our high limit going to be? 10,000. We hope that they're not in the store 10,000 minutes, but just going all the way up to there. Our mu is 45. Our standard deviation is 12. Somebody punch that in the calculator, and that's going to tell us the probability that the shopper is in the store more than 39 minutes. .69. So about 69% of the time they're going to spend 39 minutes or more in the store. And again, if you draw the little graph, you can see that 39 is below 45, so it should be higher than 50% of the time. 0.69 is higher than 50% of the time. Skip over some of this. I'm just going to, just real quick, just talk about sketching the graph again. Same problem. Between 33 and 60 minutes. I want to sketch this graph. We got our normal curve there. What's going to go right in the middle? What goes right in the middle of your graph? The mean. And the mean this time was 45. So every time, just put the mean right there in the middle. That was our mu. Our sigma was 12. If we wanted to draw the graph, draw out a good graph, all we're going to do each time is add 12 to that. So 12 plus 45 is 57. 12 plus 57 is 69. 12 plus 69 is 81. Go out 3 standard deviations. Go down 3. That'd be 33. 21, 9. Just looking at this, what's the probability that a shopper would stay in our store 9 minutes or less? Don't give me a probability, just tell me something about it.
Unlikely.
It's very unlikely, isn't it? It's 3 standard deviations out, so if you got somebody that walks in there, and they're in there for 7 minutes and then they walk right back out, you might get suspicious. Because they may have walked in, knew what they were going to steal, stuck it in their shirt or whatever they did, walked right back out. What's the probability that somebody's going to be in there more than 81 minutes? What's that? What do we know about it? Very unlikely also. What's the probability without going through and actually doing the math? Does anybody remember? What's the probability that they're going to be in the store between 45 and 57 minutes? Anybody remember that? 34%, right? 1 standard deviation. What's the probability that they're going to be in the store in that range right there? 68%. All right? So start to remember that empirical rule that 68, what was it, 68, 95, 99.7, is that right? Again, we could find the z-scores. With the z-scores, I don't want you changing all these into z-scores. I want you to use your calculator because it's easier. But be able to find the z-scores because we're going to have to use them later on, things that we can't just use our calculator. We wrote this down before. Let's skip over that. That just shows you how to use that calculator, which we already did. That's your assignment, page 252. 252. I did.